In this lecture, we're going to be talking about variance. First, let's define it. Let x be a random variable. Assume that the expectation of x is mu, then the variance of x is defined to be the expected value of x minus mu squared. Note that we do need to compute the mean before we compute the variance. We also define the standard deviation of x, denoted as sigma of x, to be the square root of the variance. Okay, in this example, we compute the variance of the value of rolling one die. Here's a very useful formula for computing the variance. As we'll show, the variance of a random variable x is equal to the expectation of x squared minus the expectation of x itself squared. Let's revisit the example of rolling a die and computing the variance, but now using this new formula. A very interesting corollary of the previous formula, which is one special case of what's called Jensen's inequality, says that the expected value of the x squared random variable is greater than or equal to the square of the expectation of the random variable. Moreover, these two quantities are equal if and only if the variance of x is 0, which is the same thing as saying the probability that x equals its mean is 1. Some properties of the variance. The first one is what happens if we scale a random variable. The variance of alpha x is alpha squared times the variance of x. We can also shift a random variable, and that won't change the variance at all. The variance of x plus a constant is the same as the variance of x. Very important theorem here, and it says that if we have two independent random variables, then the variance of their sum is the sum of their variances. Note that independence is a crucial assumption here. If x and y are not independent, then this formula does not hold. To prove this theorem, we will first prove a lemma that says that if x and y are independent, the expectation of their product is the product of their expectations. Finally, using the lemma, we can prove the theorem. Okay, here's an experiment that we could do. Let's flip 10 coins, assume the coins are fair, I mean 50-50 heads, tails, and assume they're independent. Let x be the random variable that represents the number of heads. What is the variance of x? We say that a sequence of random variables is independent and identically distributed, which is sometimes abbreviated IID, if two things are true. Number one, they're independent, and number two, they all have the same probability distribution. Specifically, the probability distribution for x1 is the same as for x2, which is the same as for x3, and so forth. Now we can prove a theorem. Let's assume that we have a sequence of IID random variables, x1 through xn, and maybe even continuing on to infinity. Let Sn be the sum of the first n of the xi, so x1 plus x2 all the way up to xn, and let An be Sn divided by n. So if you like, it's the mean of the first n random variables. Then, as we can show, the expectation of Sn is n times the expected value of x. The variance of Sn is n times the variance of x. Moreover, the expectation of An is the expectation of x itself, and the variance of An is the variance of x divided by n. Now let's go back to an experiment where we flip n coins, let Sn be the number of heads, let An be the proportion of heads, and we go ahead and compute all these quantities. That's a good place to stop, so I'll stop here.